Hello, nice to see you. How are you doing? Hi. Good afternoon. Nice to see you guys. So let me switch our slides and also we need to share my screen. Okay, so last time we started our discussion of ray optics and considered the basic ideas which stood behind the concepts of ray optics, in particular that light is traveling along straight line and doesn't change its direction if the medium is uniform and there is no change in optical properties of the medium. Also, if we have some interfaces or some distribution of optical constants in space, then we observe some deviation from this straight line, which is called ray of light. And we considered also reflection, transmission processes, which happen when a beam of light is hitting some surface, some interface. So what is important to mention that when we have penetration of light from one medium to another, as shown here on this figure in the left side of the slide, two mediums with different refractive index. So if we consider, for instance, medium 1 air with refractive index like N1, that would be considered as equal to unity, quite close to free space. And then when it goes to some material, let's say it's some glass, then the speed of light reduced by the factor which is determined like by refractive index of this second medium, which is always larger than unity. So that's why speed of light is reduced with respect to speed of light in air or in vacuum. And that is realized we are making the wavelengths shorter of the light. We don't change the frequency because that violates the conservation of energy, but we observe some shortage of wavelengths that results in smaller speed of light in this medium number 2 with a refractive index larger than unity. So that's something about this transmitted part of incident light, what we need to keep in mind, what's going on with it. So all these features of, like basic features of ray optics, they are explained in the scope of so-called hygiene model, which hygiene's principle, which considers information like previous information about wavefront. So let's say this is our previous like initial wavefront of electromagnetic wave. And so it's like plane and spherical wavefront. So once we know information about waveform, we can consider points located close to each other all over this wavefront as point sources of new spherical wavefronts. So if we deal with a point source of light, we always get like in uniform medium, which we consider by definition also, we get spherical waveform. So they are considered as generators of such new spherical wavefronts of light and light electromagnetic waves. And once, let's say, some time interval delta t is given, and we want to know where the new wavefront will be positioned within this time interval, it is necessary to consider distance this new spherical wavefront is traveling during this time interval, which is speed of light times time interval delta t. The same goes for here. See that this is part of this spherical wavefront, and actually this is the radius because it's distance from the origin, from the center of this new spherical wavefront to its actually edge, which is reached at the time interval delta t. So here c is considered speed of light in vacuum, in free space, but obviously if we have some other medium, the speed of light will be smaller. So once we consider the position of this new, like many spherical wavefronts in time interval t, the tangential curve which connects all these waveforms, it will give us the new wavefront of the initial electromagnetic wave. So considering these principles, it is possible to show and explain all these laws of reflection and refraction. So it's and one of approaches how you can explain the reasons for reflection and refraction going like following the laws which we considered last time. So now our goal is to understand better how we can form images when we have some optical systems. So first we will deal with mirrors. So it will be flat mirror, then it will be spherical mirror, and we will later proceed to optical lenses. But our goal for today will be to focus on properties of image formation, like features of image formation by mirrors. So let us take a look on this first figure on this slide. And we have some point object O at some distance P from the mirror, like flat mirror. So we can pick up a bunch of rays, then apply this rule for reflection when reflected angle is equal to the incident angle. And we will see that these rays after reflection from the mirror, they will kind of appear to converge out from this point, which is behind the mirror and considered as imaginary image of object O. That's what actually our how we see what's our perception of this image, that it's located somewhere behind the plane of this flat mirror. And this distance from the flat mirror to the image position is given by Q. So here for flat mirror, these distances are equal. Distance between the point object in front of mirror should be equal to the distance from flat mirror to the image position. So how do we deal with images when we have some extended objects, not just point? For that purpose, we consider some point, let's say this top point of the extended object, and we need to consider two rays which are approaching the mirror at different angles. So if we consider first ray, so this is incident ray, which goes perpendicularly to the surface of the mirror, and here we have reflected ray. So since the angle of incidence, like if we measure it with respect to normal to the surface of the mirror, then it's equal to 0. The same will be angle for reflected ray. It will be 0, so it will just go in opposite direction after reflection from the mirror. Then we can also consider another ray which hits the surface of the mirror at some angle theta. So in that case, the reflected ray will be also oriented at this angle theta. And now we have two rays which hit the surface and are reflected from the surface of this flat mirror. How do we form the image? We need to extrapolate these rays further towards the point where they intercept. So that will be the image of this point P, which we picked up at the extended object. So that will be the maximum height, like the top of the image, because this is the top, this point is the top of the object itself. And that's why we get the way how we some approach which is based on the analysis of passes of two independent rays originated from the same point, how we get image in the flat mirror. What is important to highlight here, that there is such a parameter when we have some image formation. There is a parameter which is relevant and defines how image is different from original object. So specular magnification is called, and in this particular case, specular magnification will be ratio between the height of the image and height of the original object. So here, as you see that these two triangulars, like right angle triangulars, they are identical. And that's why the ratio between these heights will be unity. But we need to highlight that this is not flipped, but straight image of the object. So we usually put, to highlight that fact, we need to put plus in front of unity. So the specular magnification of such system, which is defined by flat mirror, will be equal to plus unity. So it means plus that the image is straight, it's not flipped over, and the actual magnification is unity, means that we get real size image of the object. So with this, we also need to highlight the difference between imaginary and real image which can be formed. So I mentioned that this image of this point object and also this image of the extended object, which are formed by means of a flat mirror, these images are imaginary. So how we can define this? So for imaginary image, rays should not come through the point of image and should appear converging out from this point. So that is clearly seen here, that this is the point of our image, and rays actually do not go through this point because they are reflected from the surface of the mirror. However, it appears that these rays converge out from the point of this image. And if we have real image, which could be image like here in this spherical mirror, which we will discuss in more details shortly, then it actually can be shown that rays goes through the point of image, and in this case they really converge further from this point after the moment of their passing through the point of image, and in this case this image is considered to be real. Means it is its position is in front of the mirror, not somewhere appears as somewhere behind the mirror, which already also a sign for imaginary image for this object, because rays cannot go through the mirror, so mirror is considered to be totally reflective surface. So now we need to go in our discussion from flat mirror to spherical mirror, so which is a segment of some sphere, and there are two types of mirrors. So we will first consider reflection from the inner concave surface of the spherical mirror. So we will deal with this internal surface. Before we start to consider image formation in this spherical concave mirrors, we need to define certain features of this mirror. So first of all, we need to define important parameter is the radius of this sphere, a segment of which we consider as spherical mirror. And also here is this principal axis, which goes through the central point of the mirror and through the center of this sphere, which defines the shape of the spherical mirror. So that is the principal axis and radius of this sphere. So now let us consider in more details how we form image of an object when we deal with such inner surface of a concave spherical mirror. So as you may see here, image is located here, and rays actually come, they go through the image, and image is located in front of the mirror. So that is a real image of an object. But let's see how we get it. So again, we pick up like the top point of this extended object and consider two rays originating of like some of light, which originates from or reflected from this top point of the extended object. So first ray goes at some angle theta to the center of this mirror and is reflected at the same angle. Then another ray is, so it was blue ray, so now we deal with the red ray, which goes through the center of the sphere, which defines the radius, like its position with respect to the mirror defines the radius of this spherical mirror R. So it goes through this point. It hits the surface of the mirror at zero angle with respect to the normal and is reflected, so it comes back on the same line to the point where it was emitted from. So we have two rays. So in the point of interception of these two rays, we get the image of this top point of the object. We see that this image is kind of in the lower half of the image. So it's below the principal axis. So the object itself is higher than the principal axis and image point is below. So it means that our image is flipped over with respect to the original object, and that is should be taken into account as a sign minus in the specular magnification. So now let us try to extract from this schematic representation of image formation in spherical mirror some equation which will be called mirror equation and will help us to deal with different analysis of image formation of objects in spherical mirrors depending on the properties, like features of the spherical mirror itself, and also depending on the position of the original object with respect to the mirror. So for this purpose, let us consider first the large red triangular first. So we have this large red triangular, and here this angle theta we can express as the ratio h, height of the object, divided by distance of the object to the mirror, p. So let us write it down. Let me stop sharing for a second. We will come back here. So tangent theta can be expressed as h divided by p. So that we already keep in mind. Come back to our image. So the same angle theta will be this angle with respect to the normal, to the surface of the from the reflected beam. And this angle theta we can also determine from the yellow this yellow triangular, which gives us the tangent theta will be equal to minus h prime, which is the height of the image, divided by q, this distance q, which is the distance from the image to the mirror. Okay, let me again switch to our writing board, and tangent theta can be expressed also as minus h prime divided by q, which is distance from the image to the mirror. Okay, let's come back again. So now we can also determine this angle alpha, which is between the rays which goes from the top of the object, goes from the through the center of this sphere, which defines the shape of the spherical mirror, top of the image, and hits the surface of the mirror at angle 0. So that is the line what we consider with respect this orientation with respect to the principal axis. That's angle alpha. So from green triangular, we can write that this tangent alpha will be equal to the ratio between h minus h prime, because what goes below the principal axis that goes with minus sign, divided by this distance. And this distance will be the difference between radius of the sphere and position of the image with respect to the mirror. Also, we can show that tangent alpha, because these angles are equal to each other, can be expressed from this small red triangular. And that will be height of the image, h, divided by this distance, which will be distance of the image of the object from the mirror P minus the radius of the sphere. So that will be our distance from point C to point O. Now let us write it down. So from the yellow triangular, we got that tangent alpha is equal to minus h prime divided by r minus q. And from the small red triangular, tangent alpha is equal to h divided by p minus r. So now, first, let us consider this angle theta. So from here, we can write that h divided by p is equal to minus h prime divided by q. And that will give us h prime divided by h is equal to minus p divided by q. So this h prime divided by h is nothing else as the specular magnification, which I mentioned before. So in this case, it will be equal to not to unity, but to the ratio between position of the position of the object P with respect to the mirror, and position of the divided by the position of the image with respect to the mirror. And here we have this sign minus sign, which tells us that the image is flipped over with respect to the position of original object of which we get the image in this spherical mirror system. Now let us look closer to this angle alpha. So we can write based on these two equations, since they both describe this tangent alpha, we can write that the ratio h prime to h, which is specular magnification, is equal to r minus q divided by p minus r. So we also know that this specular magnification is given by this expression. So that will be equal to actually, I forgot here minus. So it will be equal to minus P divided by Q. So from here we get the relationship between all these distances between mirror and object, mirror and image, and also radius of the mirror. So it will be R minus Q divided by P minus R equal to P divided by Q. From here, we can, after some rearrangement, we will get 1 divided by P plus 1 divided by Q equal to 2 divided by R. So that is well-known mirror equation, which gives us the relationship between the properties of the mirror, its radius, the position of the object with respect to the mirror, and position of its image with respect to the mirror. So if we know two factors, let's say we know radius and position of the object with respect to the mirror, then we can calculate the position of the image with respect to the mirror. So let us consider this case when we have object which is located very far from the mirror. So in that case, P should be much larger than radius of the mirror, and 1 over P can be considered close to 0. Will be very small magnitude of this term, since P will be very large. So it's located far from the mirror. In that case, our mirror equation will be simplified. So we will get 1 over Q is equal to 2 over R. And from here, the distance from the mirror to the image will be given as follows. Q is equal to R divided by 2. So that is some special distance and special parameter of spherical mirror. And it's called focal distance, and the point at the distance R divided by 2 along principal axis is called focal point. So that is focal distance F. Let me share my screen. So here you see, oops, sorry. You see this particular situation. So if we have distance from the object very large, much larger than the radius of this spherical mirror, then we can consider that all rays which come to the mirror from the very distant object will go parallel to each other. And if they if they are reflected from the surface of this spherical mirror, they will meet in this focal point at the distance which is equal to half of the radius of this sphere, which forms the spherical mirror. So here you can see some kind of illustration for this, that indeed these lines, when they come parallel to the principal axis, they are reflected and overlap in this focal point of the mirror. So further they converge from this point, but that we also see from the mirror equation, when P, this distance, is very large, it simplifies to the, and we get the position of image located at the distance equal to half of the radius of this spherical mirror. So in this case, we can actually write that, so probably that was better to mark, like denote this distance as small f to be consistent with the textbook. So a capital F is just the focal point, and small f will be the focal distance. So in this case, we can a bit rearrange the mirror equation and get it in different form, which quite often is also used. So it will be 1 over P plus 1 over Q, and that is equal to 1 over F. So the sum of reciprocal distance of object to the mirror and image to the mirror should give us the reciprocal value of the focal distance of this mirror. And this is another form of mirror equation, which now you understand where it comes from, how we actually got this original mirror equation based on the analysis, like geometric analysis, actually, of the image formed by of some extended object by spherical mirror. So based on this geometric analysis, we could derive mirror equation. And considering the special case when the object is located very far from the mirror, we could show that the image will be located as distance at the distance radius divided by 2, which is focal distance of the mirror. So we can rewrite the final form of mirror equation, taking into account already focal distance as a new parameter. So now let us shortly also discuss the features of a convex mirror when we have reflection from the outer surface of the spherical mirror. Let me share again my screen. So in this case, we also follow the same principles of building the image as we did before. So keep in mind here that this spherical mirror also possesses this two characteristic points. So first point is the center of the sphere, which forms this spherical mirror, and second focal point, which is located at half distances of the radius from the mirror. So now we have our object that is positive distance p, which is left side from the mirror, and consider some distance to the image. How do we form the image? Again, we pick up this top point of the object and draw two rays, which will follow the reflected rays, will follow laws of refraction. And then, since in this case it's impossible that rays go through the image point, so we are talking about imaginary image, but because of this extension of these two rays toward interception, we get the point where it appears that reflected rays converge from. And that will be our image. In this case, we see this image is upright, so we don't flip it over. And it will be located at distance q. So this mirror equation, which we derived for first case when we considered reflection from the inner surface of the spherical mirror, is also applicable for reflection from the outer surface of the mirror. We just need to keep in mind that values for like the signs of distance of the object and to the mirror, and distance of the image to the mirror, because that is important. Eventually will make a difference in your calculations. So with this, that's pretty much everything what I wanted to tell you about image formation in mirrors. We considered today flat mirror and spherical mirror based on the detailed analysis, geometric analysis of this image formation of an object with spherical image, a spherical mirror. We managed to derive the spherical mirror equation which is applicable for spherical mirror. And we have shown that if distance of the object and radius of the spherical mirror are known, then we can calculate easily using this mirror equation the distance from the object to the image. Also need to recall that in case if object is located very far, all rays are coming parallel to each other and parallel to the principal axis. Considering that our object is located on the principal axis. And the image is formed at the distance equal to half of the radius of the sphere. So our next goal will be to learn about image formation in lenses, which are based on not reflection, but refraction. Because then we will have to deal with rays which penetrate inside into the lens material medium, then it will go out. So we need to take into account how much these rays will refract inside the lens, and then it will give us a possibility to form image in optical systems, which is based on lenses, which is a bit different from mirrors, but still the concepts and approaches for building images are quite similar, and we will discuss them during next lecture. Okay, let me stop sharing. If you have any questions, you're welcome.
In general, it's kind of informative. Thank you for the lecture.
You're very welcome. See you next time. Take care. Bye-bye.
Goodbye.
Thank you. Goodbye.
Bye. Have a good evening.